Welcome to another session of multivariable calculus class. Today we are going to discuss about the application of double integrals. Last class we have come across the double integrals and polar form of double integrals. First of all, let us see how we can find mass of a lamina. So suppose a lamina occupies a region R in the plane and the mass density of the lamina at a point x comma y in R is given to be as rho xy, where rho is a continuous density function. So whenever the density function is given, how we can find the mass of the lamina? It's nothing but this formula, m equal to double integral over R rho dxy dA. And we can find how we can find this one. So there are various cases we can discuss. The first one is the charge per unit area. Density is given as charge per unit area. Then also we can use the same formula. So here it's given as the density number, population density. There too we are having the density function. We are using the same formula here also. For example, we are given a problem. Find the mass of a lamina occupying a triangular region R with vertices. So vertices is given. So let us plot it. Okay, first vertices is 0, 0. Okay, no problem. It's the origin. Second vertices is 2, 0. 2, 0 means somewhere it may come here. So 2, 0. Next one is 0, 2. So 0, 2 somewhere here. So 0, 2. So our triangular lamina is something like this. And its mass density at a point xy is given as x plus 2y. So what we want to do is we want to find the mass m equal to double integral over R of rho xy dx dy. That's our area, right? Now here means we can have your x and y is ranging from here to here and y is ranging from here to here. Like that also you can consider. So for easiness we can go for polar form also. So polar form it will become m equal to integral over double integral over rho xy will become rho r theta into r dr d theta. So we can make use of that too. Here we think polar form is easy because whenever you are having your theta is here theta means 0, here is pi by 2. Now your r value is ranging from this 0 to 2. So you can easily have this calculation and put x equal to r cos theta, y equal to r sin theta. See, here is a picture is given. Y equal to 2 minus x. So we can find it. See, here they are used directly. That is integral over r rho xy dA. That's equal to integral 0 to 2. Integral 0 to 2 minus x. They haven't used the polar form. Directly they have done. You can try in your polar form also. Then x plus 2y dy dx. Then just integration. We will get it as 4. So this is first example. You can go for second example. Electric charge over a region. An electric charge is spread over a region R lying in the first quadrant and inside the circle. Find the total charge on R if the charge density measured in coulombs per square meter at a point xy in R is directly proportional to the square of the distance between the point and the origin. So let us see from a origin to a point is here xy. So what is the distance connecting these two? So region is given. So you can use the Euclidean formula. So that is 0 minus x square, that is x square plus 0 minus y square, y square. So this distance is square root of x square plus y square. Now what is given is uh, measured in coulombs per square meter at a point xy is directly proportional to the square of the distance. So square of the distance. So this is square. Now it's given that rho is proportional to x square plus y square. So directly proportional. So we can find rho is equal to some k into x square plus y square. Now you have got your rho value or the rho function, density function. Now we can see what is the region at which we want to integrate this function. That's given that it is from this circle. First quadrant intersect this circle in this fashion. In this region only we want to find integral over rho dx dy. See, in this case we can go for the polar form, I think. See, here they have done, it's in polar form, that is integral over r sigma xy dA. That will become integral, first one we are finding x value, so x value, so x is ranging from 0 to 2, so x is ranging from 0 to 2 is given. Next thing is our y value. Y value is ranging from this side to here. So here means is equal to 0. Y equal to 0. Equation of x-axis, right? So y equal to 0 I have put. Then from here to here, what is the point here? It is a point on this curve x square plus y square equal to 4. So y is nothing but y square equal to 4 minus x square. Right? So y is equal to square root of 4 minus x square here, obviously positive. So it is square root of 4 minus x square is given. Now we want to integrate this with respect to dy dx. See here x square plus y square is coming. So we can easily go for the polar form. What is x square plus y square? You will get as r square. So our formula reduces as double integral. You can see what are the limits coming, k r square, right, into r dr d theta. Right, now what should be the limit of this integration that we want to check. So first of all, theta I have put r here. So what should be the range of r? R is ranging from 0 to 2. So 0 to 2 is our r variation. Next is theta variation. Theta is varying from here to here. That means 0 to pi by 2. So we want to calculate this integral. That is k into r cube dr d theta. Very simple one, right? So just we can find it out. What is the thing? You will get it as 2 pi k. So this is the procedure how we are finding mass of a region or a lamina when the density function is given. Next what we are going to do is moment and center of mass of a lamina. So moment and center of mass of a lamina, this we can have with respect to x-axis, with respect to y-axis also. So suppose that the lamina occupies a region R in the xy plane and the mass density of the lamina at a point xy in R is rho xy, where rho is a continuous density function, then the moments of mass of the lamina with respect to x and y axis are. So with respect to x axis you can have mx, that's equal to integral over r y rho xy dA. Remember the formula when you are finding the moment about the x axis means the integrand is y rho xy dA. So with respect to y axis means it should be my equal to double integral over x rho xy dA. That's the formula. Furthermore, the center of mass of the lamina is located at a point x bar y bar, where x bar minus my by m equal to 1 by m into double integral over x rho xy dA. That's my we have substituted, nothing else, right? So x bar equal to this thing and y bar equal to mx by m. So like that we are calculating it. So where the mass of the lamina is given by m equal to double integral over r rho xy dA. Let us see how we can find it. That is, the density function rho is constant on r, then the point x bar y bar is also called centroid of the region r. This means the density function rho is a constant, means then we will say that the point is a centroid of the region, right? So here whatever the problem they are asking, first of all we want to find small m, that is mass. Okay, so here is the problem given. A lamina occupies a region R in the xy plane bounded by the parabola y equal to x square, that is this parabola y equal to x square, and the line y equal to 1. So y equal to 1 means this line, right? Y equal to 1. Find the center of mass of the lamina if its mass density at a point xy is directly proportional to the distance between the point and the x-axis. So distance between point and the x-axis, that is nothing but, if this is x-axis, distance from this to here means nothing but y, right? Okay, so here is the point xy is given, means rho xy is directly proportional to y, or you can find rho xy is equal to some k into y square is given, right? Center of bounded by the parabola. Find the center of mass of the lamina if the mass density at a point directly proportional distance between the point and the x-axis. So ky. So right, like we can write. So the mass density of the lamina is given by ky. See here given, where k is a constant of proportionality. Since r is symmetric with respect to the y-axis and the density of the lamina is directly proportional to the distance from the x-axis, we can see that center of mass is located on the y-axis, since it is given. Thus x bar, since it is lying on the y-axis, x bar should be 0. Now we want to find the y bar. Now in order to find y bar, first we want to find small m, that is mass. So m equal to, by formula, see here is given the formula, m equal to this one, this formula only, m equal to double integral over r rho xy dA. So in this case m equal to rho xy dA will become double integral over ky dy dx. Now it is ranging from, see, from here to here it is ranging. First one is varying from 0 to this point, that is 1, right? Am I right? Yeah, it's ranging from 0 to 1, and you can find that from -1 to 1 also. From here to here it's ranging. Okay, so what I thought is we can find it twice, but they are giving directly, so no problem. We can find it from -1 to 1. And next thing, we want to put the y, how y is varying. So y is varying from this point to this point. This point y is equal to 1. And what is this point? This will be mentioned by the curve, right? The curve is y equal to x square. So from x square to 1. So the variation is from x square to 1. Ky dy dx. K is a constant. You can integrate y. That is 1 by 2 into y square. Put the limits, and you will get a function in. You will get a function in x, right? So we can find that integral also. So at last you will get it as 4k by 5. So you have got your m equal to 4k by 5. Right. Now we want to find what is your y bar. So y bar is given as, see, y bar is given as by formula, see, y bar, this is y bar, y bar is equal to mx by m, that's equal to 1 by m into double integral over r y rho xy dA. So we can use this formula here, right? So y bar is equal to, what you are getting is, see, y bar is equal to 1 by m into double integral over r y rho xy dA. So y into ky into dy dx, where r is ranging from -1 to 1 and x square to 1, right? So again we can find that simple integral, because rho xy, you have got it as a constant, you can take it outside, then whatever is coming is y into ky, that is k, we can also take it outside, so you're getting y square. So 5 by 4 into double integral over -1 to 1 integral over x square to 1 y square dy dx. So we can integrate that, you will get it as 5 by 7. Therefore the center of mass of the lamina is located at 0, 5 by 7, because already we have said that since it is symmetrical, its x bar is should be 0, that is the point lies on the x-axis. Now we have find what is the y coordinate also. So the center or the center of mass of the lamina is at the point 0, 5 by 4, sorry, 5 by 7. In a similar fashion we can have the moment. So moment of inertia. The moment of mass of lamina mx and my are called the first moments of the lamina. So mx and my are called the first moments of the lamina with respect to x and y axis. We can also consider the second moment, that is the moment of inertia of a lamina about x-axis. So it can be asked that find the second moment. So find the second moment means moment of inertia. First moment means the moment with respect to x and y axes. So ready-made formula is given. The moment of inertia of a lamina with respect to the x-axis, the y-axis and the origin. So with respect to x-axis is given as ix. So ix equal to double integral over r y square rho xy dA. You have to remember this formula. Ix equal to double integral over r y square rho xy dA. Similarly, moment or moments about y-axis, iy should be, you can easily guess now, right? R into x square rho xy dA. Right? Now about the origin. About the origin means it's nothing but double integral over r x square plus y square into rho xy dA. Right? That means it's nothing but ix plus iy. Right? It's nothing but ix plus iy. So moment about origin means you can directly calculate as a double integral, or else you can have your moment about x-axis, moment about y-axis, and just add it. So here is one example. Find the moments of inertia with respect to the x-axis, y-axis and the origin. Okay, everything they have asked. So with respect to x-axis means double integral over r, we want to find what is the density function, right? Y-axis of the origin of a thin homogeneous disk of mass m and radius a centered at the origin, right? So a thin homogeneous disk is given which is centered at the origin, that is 0, and disk of mass m and radius a, its radius is going to be as a. Then we are asked to find the moment about x-axis, y-axis and origin, right? Now with respect to x-axis, we know the formula as double integral over y square rho xy dA, right? Now that will become y square, you can take this in polar coordinates also, that is double integral over instead of y square you are having r sine theta square. Now rho x, y should be rho xy. So rho xy is going to be as m by pi a square, mass by this area. So this is how you got is mass by area. Since it is thin lamina, you know that mass by volume is going to be the density, but here since it is going to be a homogeneous thin disk, we are finding its area. So that's equal to mass is m by area is pi into a square because radius is a. So this is your density function. So you can easily go for polar coordinates and we can integrate this part. So it will become r cube sine theta dr d theta. Sorry, sine square theta dr d theta. So it's very easy one to calculate. So we can have sine square theta can be written as, just you remember this, sine square theta is equal to 1 minus cos 2 theta by 2, right? Just you remember this. So you can have sine square theta as here 1 minus cos 2 theta by 2, that 2 along with this 4 will become 8 pi, right? So only this thing you want to remember here. So m a square by 8 pi into theta minus 1 by 2 into sine 2 theta 0 to 2 pi, that's equal to 1 by 4 into m a square. So the answer is 1 by 4 into m a square. So similarly we can find what is iy also, but with respect to symmetry these both should be the same. So with respect to y also you will get 1 by 4 into m a square. You can check it. First you find mx only, I have find it out. You can go for my, then check whether this is also coming as 1 by 4 into m into a square or not. If this is the case, you can go for the moment about or the moments of inertia about origin also, that is the sum of these two. So get it as 1 by 2 into m a square. Now radius of gyration of a lamina. Have you remembering from your physics class you have studied what is radius of gyration? Radius of gyration means, suppose you have got a body here and here is our axis. Now suppose this we are assuming that the center of mass of a body is this. Okay, center of mass of a body is this. Now if you're finding the distance from this axis to this center of mass, we'll get this distance as r. Now this distance is called radius of gyration of this lamina. So first of all we are finding the center of mass of the lamina and finding the distance from the axis to the center of mass. That distance is called radius of gyration of a lamina. And by formula we are having mr square equal to I, where I means moment of inertia, m means mass. So m means mass, I moment of inertia, then r means radius of gyration. So you can easily calculate radius of gyration as square root of I by m. From this you will get r square equal to I by m. Therefore r equal to square root of I by m. So here is one example. Find the radius of gyration of the disk of example 4. Okay, just before we are dealing with one disk now, with respect to the y-axis. So what you are having is, previously we have taken this disk, example 4 one disk we have taken. So we want to find this radius of gyration, right? So we have assumed that its density is m by pi into a square, right? So we can make use here. Okay, so Using the result of example 4, we have IY, right? This we have already calculated. From previous example, you have got IY is equal to 1 by 4 into M into A square. Therefore, using equation 6 means radius of gyration equation, R equal to square root of IY by M, right? From y-axis only they are asking. So we want to find the inertia about moment of inertia about y-axis. So x bar is equal to IY by M square root of, right? Now IY, it is 1 by 4 into, that is square root of 1 by 4 into M A square by M. So we'll get that it is 1 by 2A, right? Now in example 5, we have used the customary notation x bar double bar, right? So we are using x double bar for the radius of gyration of the lamina with respect to the y-axis, and radius of gyration of lamina with respect to x-axis if we want to find means we can use the notation as y double bar. Okay, so this is for today's class. Thank you for your patient listening. So today we have discussed about how we can find moment of inertia and mass of a region using double integrals. So hope you understood. If you are having any queries or any doubt is need to be clarified from my side, please free to ask. Thank you, and thank you for your patient listening. Thank you.